Okay, today we're going to talk about goals and preferences. So here's a nice quote from Alice's Adventures in Wonderland. Alice went on, "Would you tell me, please, which way I ought to go from here?" "That depends a good deal on where you want to get to," said the cat. "I don't much care where," said Alice. "Then it doesn't matter which way you go," said the cat. So the point of this, if you don't have preferences, it doesn't matter what you do. The only reason for doing something over another is because you prefer the outcome of one over the other. You have preferences over the outcome. If you have no preferences, it doesn't matter what you do. Okay, so what we're going to do is we're going to go through now this idea of, we're going to look at these dimensions that we looked at the very start of this class. So we did strips planning, it was deterministic, fully observable, we did features, and we looked at indefinite stages or infinite stage, and we had goals, right? And so this is the case we're looking at for strips planning, and also it was the simplest of all of the other cases. So what we're going to do now is we're going to look at this other case, is we're going to now have the difference between this is now we're going to look at both stochastic and partially observable. It's going to look at both of those two things. And then we're also going to look at just finite stage. We're also going to look at complex preferences. So it's stochastic, partially observable, finite stage, and complex preferences. Okay. So what we're going to do is look at an agent should do. So what we studied the very first class, looked at what an agent should do, and what an agent should do depends on the agent's ability, what options are available to it. And also we're going to look now at the agent's beliefs. So what we've looked at so far is how prior knowledge and observations can update an agent's belief. And what we're going to do is an agent should do now depends on its beliefs. And that's the way the world could be given an agent's knowledge. So that's what we're going to look at. That's what we've been studying with probability. And sensing updates the agent's beliefs. So we're going to use decision making under ability now depends on the agent's beliefs as well as ability. And also depends on the agent's preferences, what the agent wants and trades offs when there are risks. So often we're going to make decisions when we don't actually know the outcome of something. We've got to make actions where we have risks. Okay. And decision theory specifies how to trade off the desirability of probabilities and the probability of outcomes for competing actions. And that's what we're going to base what we're going to do now is on decision theory. So here's the idea. Here's the argument. Actions result in outcomes. So when we do actions, they have outcomes. They have consequences. And agents have preferences over these outcomes. So we have preferences, so agents prefer one outcome over another. And a rational agent will do the outcome that has the best outcome for them, and what the best outcome depends on the agent. And sometimes agents don't know the outcomes of actions, but they still need to compare actions. So we've got to work out what to do if you don't know what's going on. And agents have to act, because doing nothing is often an action we have to do. Okay, so you have to act, you have preferences over outcomes, but sometimes you don't know the consequences of your actions. Okay. So an agent may not know the preference outcomes, but have a probability distribution over these outcomes. So we're going to assume here that we're going to have a model of the world in which we can work out the probability distribution over the outcomes. And then this lottery is just this probability distribution over outcomes. We're going to call this a lottery. And we're going to write this as this. So this means with probability P1, you get outcome O1. With probability P2, you get outcome O2. With probability PK, you get outcome OK. So these O1 to OKs are different outcomes, and this PI is a probability, and they all sum to 1. So it specifies that OI occurs with probability PI. So we're going to write these as lotteries. So now what we're going to have is a utility is going to specify your preferences, someone's preferences of a possible world. So we act in the world, we can rule these possible worlds like we looked at in probability theory. But now we have preferences over them. So we're also going to have preferences over them. Okay. And each possible world has a real value utility that measures the desirability of the world. Okay. Let's define utility. So what we're going to do is define suppose the best world, we're going to call best, has utility of 1. And the worst world, which we're going to call worst, has a utility of 0. And for other worlds, any other world W, we're going to define the utility for this has these properties. We're going to look at a lottery with probability P you get the best. Okay, probably P you get the best. With probably 1 minus P you get the worst outcome. So looking at this lottery between the best and the worst outcome. Of course, if P is close to 1, this gets better and better. As P gets close to 0, you get close to the worst outcome. And sometimes the idea is sometimes you're going to sort of be able to compare each outcome to this lottery about how we do this. Okay, so when P gets to be 1, sorry, when P is 1, you get the best, but as P gets reduced, sometime you're going to start preferring U to P. So for every P less than U of W, you're going to prefer the outcome W. You're going to prefer the lottery when P is bigger than U of W. And the last one is you're indifferent between W and the lottery for when P is equal to U of W, the utility of this world. So the utility of the world is basically where you flip between preferring the lottery or preferring the outcome W. Okay. And utilities can be any real number, and we're going to linearly scale them to 0, 1 and use the above definition. So often we're going to use 0 to 100. Okay, so we're going to think about this as just some 0 to 100. It actually doesn't matter what scale you do. 0 to 100 is useful because it lets us distinguish utilities from probabilities. Okay, and different people can have different utilities. So this is not something you get by observing the world like probabilities are, but you actually have to work out what agents' utilities are. So as an example, suppose you have a robot that can wander around the lab or an area of corridors where there are stairs. And it can choose to wear pads to protect itself or not. And the idea is if it's wearing pads and has an accident, then it's going to be better off than if it didn't. But wearing pads adds extra weight, and so it uses more power. And so also the robot can choose to go the short way past the stairs or the long way that reduces the chance of an accident. Right? So you can take risks, and there might be an accident. This is not under the control of these agents. So there's a probability of having an accident. And this probability of having an accident depends on whether it goes the short way or the long way. So we can actually look at these worlds here. So there's a choice between whether you wear pads or you don't wear pads, a choice between whether you go the short way or the long way, and then there's a chance of an accident or there's no accident. Okay, so these are the 7 possible worlds. I drew it in this tree form. And what we want to do is to look at the best outcome. Okay, so we're going to look at the best outcome here. Well, the best outcome is we want it to be quick, go the short way, don't wear pads, and have no weight, have no accident. Okay, so that is so this one here is going to be the best outcome. So we're going to write that as 100. So we can find this to be the 100. So this is the utility. Okay. Now we're going to look at the worst outcome. Well, the worst outcome is so if you wear pads, then you only get moderate damage. But these 2 worlds, we have severe damage, and presumably the world where you have severe damage and you went a long way is a bit better than the one where you did a short way. It's a bit worse. So this one here is 0. So every other time now, we're going to choose with probability P, we're going to choose W5, world W5, which is the best world. And with probability 1 minus P, 1 minus P, whoa, 1 minus P, we're going to choose W6. Okay, so that's what we're doing here. And now we're going to look at each of these. So let's look at another one of these. So let's look at this now, the worst one. So now let's look at W4 here. So W4 is a bit like W6, but maybe you prefer it a little bit more. So maybe this is going to be 5. So that means here the probability that we're concerned here is 0.05. Okay. The other bad ones are are the ones we have moderate damage. So suppose moderate damage is not nearly as bad. So if you look at how much you prefer, if there's a lottery between severe damage and being really quick, then maybe it's around, say 40 and, right, whoops. Maybe it's around 40. Okay, that's for this one. And this one's pretty similar, except we come a long ways, so it's slightly best. So maybe this is 35. Okay, so we're going to go through each of these and try to compare the different utilities of things and the weights here. All right. So now we're going to look. So now we have just worlds, but now we have to go and have probabilities, and we're going to combine them together. So now what we're going to do is define the expected value of a function of possible worlds. And here the function of possible worlds we're going to use as the utility. And this is just the average value, weighting possible worlds by the probability. Suppose f is the value of a function f in world w. So we're going to write f of w. And this big omega is a set of all worlds. Then the expected value of f is, we're going to sum over all the worlds, the probability of the world times this value of the world. So if this is heights, and this is might be the average height, we're going to look at how much for each height, the proportion of people in the world, and we're going to multiply it by the height. We get the average height, right? So it works for anything we're going to average. And we're also going to define conditional expected value. We're just going to condition on E. So we're going to look at just as the worlds entail E. This one here has this constant. Remember, the worlds that entail E are now going to be multiplied by this constant. And we're going to just have this measure of E. Okay. So now we're going to redefine, we're now going to introduce decision variables as well as random variables. So decision variables are like random variables, but the agent gets to choose a value for. And a possible world is going to be a value for each decision variable and each random variable. And for each assignment of values to all decision variables, the measure of the sum of the set of possible worlds satisfying that assignment sums to 1. And the probability of a proposition is now going to be undefined unless the agent conditions on the values of all decision variables. So I'm not going to ask what's the probability of me doing something when I get to choose it, because I get to choose what I'm going to do. It's only when the agent's chosen what it's doing that we end up having a probability distribution. So here is this exactly the same thing before. And now the square boxes, now we've done here, the square boxes here, as the agent gets to choose whether it wears pads or doesn't wear pads. The agent gets to choose whether it goes the short way or the long way. So these are going to be decision variables. The agent does not get to choose whether they have an accident or not. That's something that happens, is going to be stochastic. But whether they have an accident depends on the actions of the agents. So the probabilities of these two sum up to 1. So if the agent wears pads and goes the short way, these probably this adds up to 1. Okay, so that's what we're going to do here. We're going to look at all of these as probabilities. So the agent gets to choose these, but these are random variables. Okay, so now let's finish up and I'll give you the clicker question I want you to think about for class. So often when we do decision making, so people now, there's a big problem of earthquake proofing schools. So should we earthquake proof schools? And if we earthquake proof schools, then we're going to stop earthquake damage to this school. But it's going to spend lots of money. It costs lots of money. So it has a constant decision making under uncertainty. So here's an example. Suppose the worst outcome is 500 kids die and you have a utility of 0. This is really bad if kids die. And the best outcome is no money spent and no injuries and you have a utility of 0. So we didn't spend any money, and somewhere in between that, we can do earthquake proofing. And suppose it costs $1 million. Okay, we can do $1 million in an earthquake, and it has some outcome of what's going to happen. Maybe no kids die. Okay, and suppose this has a utility of 80. I want to know what that means. Does it mean if you spend $1 million, only 20% of the students would die? Does it mean you'd prefer to spend $1 million to get the advantage of earthquake proofing if There is a greater than 20% chance of the worst outcome. You'd be prepared to spend $5 million to guarantee to save all the children, or you're prepared to spend $1 million to save 80% of the children. So go back and look at the definition of what utility means and work this out. Okay, let's stop here.